Presentation is about testing piles under existing structure, and the focus is going to be testing under existing structures, which is a unique case for testing, and it's not the usual testing scenario. We're gonna, after a short introduction just about what is a pile, what is a structure, we're gonna talk about what is so unique about testing the piles under structures. We're gonna talk about the main testing methods which are applicable to this scenario, which is gonna be the pulse echo testing with our product, the PET, and the parallel seismic test, which is with our parallel seismic instrument, and the cross-hole ultrasonic monitoring or cross-hole testing with our product, the CHUM. We're going to have time for Q&A, and I really encourage you at any time to either raise your hand with the presentation or write some text with your questions, and Mr. Zulfikar will summarize that, and we'll have time for Q&A at the end. So some definitions. A pile is a slender deep foundation element. It can be precast or cast on site. When I mean slender, it means that it's much longer than it's wide. That's something you all probably know already. A superstructure for this presentation, or a structure, is just anything connected on top of the pile. It can be a beam, a slab, a column, or the complete structure, anything which lies connected firmly to the top of the pile. The typical scenario for piles under a superstructure is that they are usually old. We don't have the S-made documents, or we have a very partial information. And also, typically, the access is problematic. Not all cases are always correct, but this is a typical scenario. Here's a typical scenario. We have a bridge. We can't see the top of the piles. We have no idea about how long the piles are. We just maybe want to expand this bridge, or we just want to know when maintenance is due and we have no information. We want to gather it. Another scenario here, this building needs to be expanded. Very little information about the pile exists. For some reason, documents are lost, and so on. Another example, here the side of the piles is visible, but we have not enough information for any future plans about this bridge. So what are the challenges that we're facing when we're going to test the piles? Well, first of all, we have limited or no information about the S-made length of the piles, the concrete type, the installation method, the type of the foundation. It can be a footing. We just can't know from the top. Another thing is that the existing structure interferes with the pile. It's actually changing its properties, the mass, the impedance, the way the waves are flowing. We have a small sample. Usually the strength of pile testing is when you test a lot of piles and you can compare them one to another. But in this case, under the existing structure, we have a limited amount of piles to test. The physical access is also sometimes tricky, which makes testing conditions less ideal and harder to get quality information. Underground utilities, such as basements and things like that, can also interfere. Sewage lines, which we don't know about. All these things are adding more and more challenges to testing under existing structures. The main integrity methods that we are going to discuss today for testing under structures are, first, the pulse echo method. It's a very known and very popular method backed by this ASTM standard. It is, let's say, so-so. suitable for testing under existing structures. In many cases it is, but there are many caveats to watch. The parallel seismic method is definitely suitable for testing under existing structures. In fact, it was designed for testing in those scenarios. The ASTM standard for this test method is currently in final ballot on the ASTM main committee, and it's going to be ready, I believe, within a month. The technical contact for the parallel seismic standard is Dr. Joram Omir, a co-founder in our company. The third method we're going to discuss is the cross-hole ultrasonic monitoring or logging, also called CSL. This method will hardly ever be suitable for testing under existing structures, but I still do want to mention it because there might be some cases where this could be applicable. So it's good to have this somewhere in the back of your mind that it's possible. So without any further delay, let's go into each of the testing methods and see how it's applicable. Let's go. So first, we're going to discuss the pulse echo method, PEM, with our product PET. We're going to watch a short video, a 3 minutes video, and then we're going to see how this method can be modified and applied to testing under structures.
PET, Pile Eco Tester, Low Strain Impact Testing. The mission: test the integrity of 12 concrete piles on this construction site. The tester goes to the first pile and prepares the top for testing. A small amount of special putty is attached to the bottom of the PET. The PET is pressed against the pile top. The top is lightly hit with the hammer. A compressive wave travels down the pile and is reflected back from the toe. The blow is recorded on the screen. Good pile. The next pile has a defect that reflects the wave. The reflectogram on the screen shows a necking at a depth of 5 meters. The test results are now analyzed in the office and the report produced. The PET, your compact yet powerful tool for testing the integrity of deep foundations. Thank you.
Okay, and we are back. The next thing I want to show you is the PileWave program. The PileWave program is a simulation of wave propagation in piles, which just gives some background about how this method works. So when you go to the PileWave application, you can see that screen. On the left, we see the shape of the pile. The main pane here is the way the waves are traveling down and up in the pile, and the top pane is the head velocity of the pile. So we can see that when we hit the top of the pile, let's do that with some delay. Okay, so this is the hammer impact. and a compressive wave is traveling down the pile. The wave keeps on traveling until it reaches the bottom of the pile. At this stage, it is converted from a compression wave to a tensile wave, and then it reaches back the top of the pile, pulls it down again, and that's about it. If we have some kind of a defect in the pile, for example, a necking here, that's also going to reflect the wave. So some part of the wave is going to be reflected from this defect and from the bottom of the defect. And then the rest of the wave travels all the way down and back up, and we see the echo from the top. If, however, instead of a necking, we would have a bulge here, this part, instead of traveling down, representing a compression wave, will be going upwards, like that. So now the wave goes up and then down. And again, the rest of the wave travels down and reaches the bottom of the pile. So that's really a very, very quick overview of that. I just want to mention one more point. In case there is a skin friction, let's reset that to a cylindrical pile. In case there is some skin friction, which is usually the case when the pile is not in air but in soil, the wave will become weaker and weaker. And we will have a very faint, if any, echo from the toe of the pile. In this case, we apply some amplification so that we can see the pile as if it was in air. Okay, and I'm going to go back to the presentation. Okay, let's see some real life examples of real piles. So this would be a good pile with the trigger hammer, the hammer trigger, and the echo from the bottom at 10 meters. This would be a pile with a necking, and this would be a pile with a bulge. If we wouldn't have a superstructure, like, let's call it regular testing, the sonic test can find the pile length, inclusion of foreign materials if they are large enough, horizontal cracking, joints and stage concreting, sharp changes in the cross-section of the pile, and even distinct changes in soil layers. However, in our case, pile length is the only thing we can expect. There we go. So how do we adapt the pulse echo method to test under existing structure? I'm going to get over that very quickly for those who did get it. So when the top of the pile is round and the column is square, we can sometimes get some kind of a notch there. For example, here, in this case. Can you hear me, everyone? Can you see the slides now? Okay.
Yes. Of course.
We can test here. Great. In this case, we have some access here to the top of the pile, or here. The other alternative, if we don't have access to the top of the pile at all, is to cut a small notch at the side of the pile. Like in this case, this is a part of a retaining wall, and this notch was cut into this pile. Here's another example with the sensor inside, so you can see the side of the notch. It's constructively neglectable compared to the size of this pile or column. And in another case, another pile in a retaining wall, and a small notch was cut there. You can see the hammer for proportion. This gives you the good option for testing with the pulse echo method. Okay, and the first rule is when testing under an existing structure is to lower your expectations. The pulse echo method is highly affected by the waves from the superstructure. And note that when you hit the pile and you're creating a compressive wave going down, the same wave also travels up into the superstructure, and it can be reflected from any edge. It can be reflected from the ceiling or from the side of the beam. It can go sideways, upwards, anywhere. Moreover, the wave going into the superstructure is not attenuated as much as the wave going down. And there's no way of telling what the waves are doing in the superstructure. It can be very misleading. For that, more than one pile, ideally many more, should be tested so that we can check repeatability. The assumption is that the piles are going to generate a unique signal, while the superstructure at each location is going to generate something different. So that if we do get a repeatable result, we can assume with some certainty that it is really the pile, and we are not just testing the ceiling or the beam. Never trust the results of just one pile. The only real expectation here is the length of the pile. We don't get much more information, if at all. To summarize, we recommend to try. If it works and we get reliable, trustworthy information, great, because the alternative is much more expensive and slow.